Welcome to the engineering design presentation from the Bern Formula student team from the University of Applied Sciences Bern. This part is about the tractive system and drivetrain. My name is Felix Sarbach and I'm the CTO of the team. After a short part about the controls in the system, our inverter and the central computing unit that we use, I will be going more in depth about the controls and setup, heat dissipation, and the efficiency of the different tractive system and drivetrain parts. Our control system is built rather simple. We have the battery, we have our central computing unit at the top right, the inverter in the left, and two motors. The central computing unit receives all values from all sensors, as well as the BMS, that we can evaluate a goal speed for each motor. It gives the goal value to the inverter. The inverter then can take the high voltage from the battery and give it to the motor in the current, voltage and frequency that we can drive as efficient as possible. The motors have a resolver mounted on them that the inverter always knows what position they are in. The inverter this year is a new product that we have not any experience with. The new inverter from Lenze is prefabricated and pre-shielded, that we have no electromagnetic interference problems. We do not need to construct or evaluate special cooling systems as in an open inverter as in previous years. One inverter will work for both motors. We have the ability to communicate via CAN bus with the central computing unit. Our central computing unit is from SpeedGoat, which is a really powerful target machine. We can program it with MATLAB Simulink, which can give us a simple and easy interface. The central computing unit communicates, as mentioned, with one line of the CAN bus, only with the inverter, and one line of CAN bus for all the sensors, switches, lights on the car, as well as to receive all data from the battery management system. Considering that our electro team consists of only 3 people, we were not able to implement a very clever torque controlled system. So we went for the next efficient idea, which is just to have a goal rotation speed that takes in consideration of the current high voltage battery temperatures and voltages, as well as the gas pedal position. If the battery is very hot, then we can limit the maximum current. We were able to avoid a difficult regulation system by using the one integrated in the inverter that will automatically balance the current and voltage to each motor individually and give them the frequency that the SpeedGoat gave the inverter. Implementing a torque control could be a goal for future years, but considering our team size at the moment, it is not realistic and not really high on the priorities. Heat dissipation. Our high voltage battery is air cooled. That gives us the possibility to use less water on the car and air has better access to each cell. Thus, we can cool it more efficient and lighter. Furthermore, each motor has its cooling circuit, and the inverter is connected with one cooling circuit of a motor. And this is how it looks like in the car. What is not shown here are the water pumps, since they do not generate heat significantly or do not aid the cooling. In the center, the large grey block is the high voltage battery. It is air cooled and there are no water pipes going directly to the high voltage battery. On top of it is a smaller grey block, that is the inverter. It gets its water after it has passed through the motors, since the inverter is less temperature sensitive than the motors. Afterwards, the cooling system goes to the side pods, where the radiators and fans are positioned. The side pods are in shape of a wing. Each wing has one radiator and one fan mounted inside. As mentioned, the battery is separately air-cooled. If we would cut through the side pod, this is how it looks like. We tested several simulations, airflow simulations, of the side pod with the inlet in the bottom half or in the top half, as well as the outlet on the top and then the bottom, to evaluate which inlet and outlet, how much downforce to drag ratio it gives us. In the end, we decided for an inlet at the top as well as the outlet at the top that can give us a maximum downforce while avoiding little disturbance for future or for rear coming aerodynamic parts. Now to the efficiencies. The whole energy starts in the high voltage battery, where it goes to the high voltage box. The high voltage box in this case can also be used to simplify in the schematic wiring and connectors. Afterwards, it goes to the inverter, which splits it up for the motor left and right, and each individual gearbox. The motors are positioned in the wheel hubs, so there is no differential except for our electronic differential that we use. This block diagram is based for the efficiency calculations that we will be going through, starting with the high voltage battery. To test the thermal efficiency of the battery, we made a discharge test. For that, we discharged them with 60 ampere continuous, and since the batteries are 5 in parallel, it would be 12 amperes each cell. That is without cycling, since 60 amperes is about the average that we will have during a race. During that test, we logged the energy, the cell temperatures and voltages until the cell is empty, or until the cell overheated hotter than 60 degrees, since afterwards the test would be unsafe. With an estimation of the specific thermal capacity of the cells, we can calculate the inefficiency or the efficiency of the batteries. Adding to that, the battery itself is a large temperature inertia, since it is also very heavy, but we are able to estimate the efficiency to a 98%. After that, after the battery, the tractive system brings the power to the inverter. The inverter is, as mentioned, a bought product, thus giving us not much possibility to evaluate its efficiency since it wasn't given in a data sheet. But since they gave us the cooling requirements, we know how much energy it will give to the outside. It is not very clear if that could be from the low voltage system or from the high voltage, but we can assume that it will be mainly from the high voltage system. They recommend a water flow from 2 liters per minute, and it has a maximum temperature of 70 degrees Celsius inside the inverter. With that, we can estimate its efficiencies. The efficiency of the motor was rather simple, since they gave us a detailed data sheet of it. We dimensioned the cooling for the motor that we could run continuous at 89% efficiency or even a bit less, whilst the motor can have a maximum efficiency of up to 97% at ranges at speeds of 4000 turns per minute and a torque of only 2 Newton meters. But generally, assuming that the motors will be using high torque and medium to high speeds, it is well in the 94 to 95% range. Since the gearbox is self-developed, it is difficult to estimate a correct value. There are several dependencies, for example lubrication, how much we have run it in, the tightness of the sealing giving friction, and quality of the gears, depending on how the gears were paired to each other. We had the possibility to measure each gear separately and then paired them to each other, which gave us another 20% less friction on the gears, which means that the inefficiencies are 20% lower considering only the friction between the gears. That will give us a realistic estimation from somewhat between 92 to 95%. With simulation with KISSsoft software, optimal gears with our goal roughness and perfect shape would have an efficiency of 98%. But since that value is barely achieved, we stuck to 92 to 95%. Adding all efficiencies together, we can estimate a 97% of the battery, the same for the inverter, 90% efficiency of the motor, and 92% in the gearbox. That gives us a total efficiency of 77.9%. Considering that the maximum power that the Formula Student cars may give is measured after the power leaves the battery, the thermal inefficiencies of the battery does not have to be considered for the drivetrain efficiency, yet it still is good engineering practice to take or to choose an efficient battery. So considering only the inverter, motor and gearbox, which is 97, 90 and 92% efficiency, that gives us an 80% efficiency from all power leaving the battery.